So let us now reap some benefits of this proposition 2. Remember at the beginning I asked the question, if you have two groups and they have the same number of elements, is there any way to say that they are not isomorphic? So here's a corollary to this proposition. If G and H are isomorphic groups, then for any positive integer n, G has the same number of elements of order n as H. Not only they must have the same number of elements in total, but given any possible order, they must have the same number of elements of any given order. Why is that true? Because if they're isomorphic, there's an isomorphism phi between G and H. And isomorphisms are injective. So for any given element, the order doesn't change. The order of G is equal to the order of phi of G. So if G had 3 elements of order 7, then H must have 3 elements of order 7. Right? Because so every element of order 7 in G will be mapped to element of order 7 in H, and on the other hand, using the inverse isomorphism, every element of order 7 in H will be mapped to an element of order 7 in G. So you must have the same number of elements. So let's now do an example. Remember, I wanted to see if Z mod 4z is isomorphic to Z mod 2z cross Z mod 2z. Right? Note, they both have the same number of elements, so they both have the same order. 4. But let's look at their elements, the order of their elements. So, in Z mod 4z, we have the following elements. 4z, its order is 1. 1 plus 4z, we already did this calculation, the order was 4. 2 plus 4z, the order was 2. And 3 plus 4z had order 4. Let's look at the orders of elements in this group. 2z, 2z has order 1. 1 plus 2z, 2z. Alright, let's try that. If I add this element to itself, I get 2z, 2z, so I get the identity. So the order is 2. What about 2z, 1 plus 2z? If I add this element to itself, I get 2z, 2z. So again, I get the identity. So it's also of order 2. And finally, this, right? If I add this to itself, coordinate-wise addition, I get 2z, 2z. So the order is 2. How many elements of order 1 do I have in both groups? It has to be only 1. Fine. How many elements of order 2 do I have? 2, 2. 2, 2. Different number. I have different number of elements of order 2. So these groups are not isomorphic. As, oops. Have different numbers of elements of order 2, they are not isomorphic. Not. Okay, two groups of order 4, but they're not isomorphic. Okay. Okay, let's prove some other properties of homomorphisms and isomorphisms. And some of them I'll leave to you as exercises, but some of them we'll prove. So here's one that is an exercise, so proposition 4. Actually, before I talk about proposition, let's just introduce the following notation. The range of a homomorphism phi from G to H is called the image. Denoted by I and phi. Okay, I've been talking about the range so far, but the proper terminology and for group theory is the image. And the proposition that I would like you to prove is the following. It's an easy proposition, proposition 4. Let G, H be groups, and phi from G to H be a homomorphism. Then the image of phi is a subgroup of H. Okay? Of course, the range of a homomorphism like this lies, it's a subset of H. I want you to prove that it's a subgroup, so that it is actually a group. Remember, what that means is to show that given any two elements in the image, if I multiply them as elements of H, I get an element in the image. The identity is in the image. And given any element in the image, its inverse is also in the image. Okay, proposition 5. Let phi from G to H be a group homomorphism, be a homomorphism. So G and H are groups. If G1, G2, and G commute, then so do their images. Okay, this is quite an easy proposition, so let's prove this. Proof. So I want to know, so phi of G1, phi of G2, I want to see if this commutes. So because phi is a homomorphism, I can just stick G1 and G2 inside. Now because G1 and G2 commute, I can switch their order inside phi, and now again phi being a homomorphism tells me that this is this. So we're done. Phi of G1, phi of G2 is equal to phi of G2, phi of G1. So they commute. Okay, so we get a corollary to this very easy proposition that says the following. So corollary 6. So let G, H be groups. Let phi from G to H be a homomorphism. If G is abelian, then the image of phi is abelian. Is an abelian subgroup of H. Is abelian. You already know it's a subgroup, so it is abelian. Right? If G is abelian, then any two elements commute. So phi of these elements will commute as well. So the image is also abelian. So in particular, if in addition phi is surjective, then H is also abelian. Why? Because if phi is surjective, then the image of phi is equal to H. So, because image of phi is abelian, then so H will be abelian. Okay, so we have talked about the image. Let's talk about something else. Sort of an analog of the image, but on the G side, namely the kernel. So let phi from G to H be a homomorphism. So we define kernel of phi to be all these elements of G that are mapped to the identity in H. So this is something like the zeros of a function. It's an analog of zeros of a function. So normally when you, for example, look at the function from R to R, x squared minus 1, then 1 and negative 1 are mapped to 0. We sometimes call it the zeros of the function. But the analog of a zero, it would be the identity in the group H. So all these elements of G which are mapped to the identity are like the zeros of this homomorphism. And the set consisting of all of them is called the kernel. This is called the kernel of phi. Okay, and there's another. Where is the kernel contained? Is it a subset of G or a subset of H? Well, by definition, it's a subset of G. So here's proposition 7, which again I leave to you as an exercise. Kernel of phi is a subgroup of G. Image of phi is a subgroup of H. Kernel of phi is a subgroup of G. Now, you might know these notions of kernel and image from linear algebra. And you might wonder if there's a relation here. When you think about it, any linear transformation from every vector space is a group under addition. So if you have a linear transformation from vector space V to vector space W, it turns out that the linear transformation is a group homomorphism from this one vector space, which you can treat as a group under addition, to the other vector space, which you can treat as a group under addition. So then the notions of image and kernel coincide. The notion of kernel in our class coincides with the notion of kernel in linear algebra, and the notion of image in our class coincides with the notion of image in linear algebra. Okay, however, I wanted to finish with the following proposition that says the following. So let G and H be groups, and let phi be a group homomorphism, be a homomorphism. Just like in linear algebra, there is sort of an easy way to check if a homomorphism is injective. Namely, you just check if the kernel is trivial. Then phi is injective if and only if the kernel of phi is just the identity in G. Let's prove this. So, proof. One direction is obvious, okay? You might want to pause the video and think about which direction is obvious. So, the direction that is obvious is this one. If phi is injective, then it can only map one element of G to the identity in H. right? Because injections map different elements to different elements. So only one element can go to the identity. But you know what element goes to the identity. By proposition 0, this has to be this element. Must be the identity in G. So kernel of phi is just equal to the identity in G. So the thing that you need to prove is the converse to this statement. So conversely, suppose kernel of phi is just the identity. So assume phi of G1 is equal to phi of G2 for some G1, G2, and G. Okay? You're trying to prove injectivity, so if you assume that G1 and G2 go to the same element, then you have to prove that G1 is equal to G2. So want to show G1 is equal to G2. How are we going to do that? So we have this. The identity in H is equal to phi of G1, phi of G2 inverse, right? If phi of G1 is equal to phi of G2, then phi of G1 times phi of G2 inverse is equal to the identity. Now this, by proposition 1, allows me to put the inverse inside. Now because phi is a homomorphism, I can collapse this expression like that. So look, so G1, G2 inverse is mapped to the identity. But by definition, elements that are mapped to the identity are in the kernel. So G1, G2 inverse is in the kernel of phi. Right? What's the kernel? The kernel are the elements of G which are mapped to the identity. So G1, G2 inverse is in the kernel. But what did we assume about the kernel? We assumed that it only consists of the identity in G. So by our assumption, we get G1, G2 inverse is the identity in G. So G1 is equal to G2 as desired. Okay? So we proved that if phi1 of G1 is equal to phi1 of G2, then G1 must be equal to G2. So the function is injected.